Well, hello everyone, and welcome to the intro to the enthalpy or calculating enthalpy of reaction. Please read this. Pause the video right now and read. So now that you have read this, we are going to go through some of the pre-lab questions together, and some of them I'm going to leave to you. So again, the goal of this lab is to calculate the enthalpy of a reaction, and I'm going to explain what reaction we're doing. Make sure you use the language in the introduction when you're answering question 1. So question 2 asks, where does the heat produced from the reaction come from? Okay. So what is the answer to that question? And if you look in the intro, it says, it is important to realize that the heat emanates from the acid and the metal because it is reacting, bonds breaking and other bonds forming, not because it is high in temperature and cooling down. So where is the heat coming from? The heat is coming from bonds forming. Hold on, my pen is... Bonds forming, as the pen never works. So bonds forming in the reaction. And since it's exothermic, this has to be greater than the bonds breaking. Otherwise, it would be an endothermic reaction. But the heat produced comes from bonds forming in the reaction. And because it's exothermic, and this is really important, the AP exam loves this question, because it's exothermic, the energy released by the bonds forming has to be greater than the energy released when you're breaking the bonds in the beginning. The assumption that we're always making, and this assumption is definitely not true, is the assumption that the heat is lost by the reaction will be gained by the water. And we know that I use a cup from Dunkin' Donuts. We know that that is not exactly true, and some of the heat may be lost to the air. And then, so we're going to talk about that later in the lab. So it says, write a balanced equation to represent the reaction of HCl with magnesium. So in the lab, which you're going to see in a second, we're going to react HCl with magnesium, and this is a double replacement reaction. Magnesium kicks out hydrogen, and remember, hydrogen is a diatomic. And you have to remember that Mg has a +2 charge and Cl has a -1 charge. So the correct formula here is MgCl2. And then we need to balance it by putting a 2 here. So this is the reaction that we're going to be doing. We're going to see that this is going to be an excess when we do the reaction. And this is going to be the limiting reactant. This is going to be all used up in the reaction. And our goal is to calculate the enthalpy of this reaction per mole of magnesium reacted. Because Mg is the limiting reactant, and you always calculate the enthalpy using the moles of the limiting. So question 5 and 6, I'm going to let you answer by yourself. These are in your notes. What I want you to do now is pause this video and then go back to Google Classroom and click on the video, it's the second video, of me doing the lab. In the lab, I'm going to do the reaction between, let me scroll back up, between hydrochloric acid and magnesium, and I'm going to record the initial temperature when these are in the cup together, and then record the temperature when the reaction is done. And I'm going to know when the reaction is done because when magnesium reacts with hydrochloric acid, it creates hydrogen, which is a gas, and it makes this bubbling sound. When I no longer hear the bubbling sound, I know the reaction is over, and also the temperature will stop going up. Because obviously the temperature is going to get hot, and then it's going to cool down because it is losing heat to the air somewhat. And there's no more heat being produced, so it will eventually cool down to the temperature of the air. So I know the reaction is over when I stop hearing the bubbling and the temperature stops going up. So pause this video now and go watch the lab. Okay, now that you watched the lab or watched the reaction, I'm going to help you with some of the math. I'm not actually going to do the math. But I'm going to sort of walk you through. I'm not gonna button press. I'm gonna walk you through how to do it. So I did the subtraction for you here, so it's 40.322, and that makes sense because it was about 40 milliliters. It was actually a little bit above 40 milliliters, and that makes sense because remember the density of things which are water is basically 1, so it makes sense that the mass of hydrochloric acid would be close to 40. So to calculate the temperature change that occurred, notice that I labeled, you would do F minus E. I labeled or final minus initial. Calculate the mass of the metal and the mass of hydrochloric acid. So you would do C plus D. And remember, the reaction is occurring inside the cup. So we must include, when we're doing the M equals MC change in T, or Q equals MC change in T, we must include the mass of everything that's in the cup. So now we're going to calculate the heat that the water gained from the reaction. So it's Q equals MC change in T. Our mass is what we got in B. So whatever you got in B, remember, we have to include the mass of everything in the cup. So the mass is what you got in B. The specific heat is 4.186. And then the change in temperature is what you got in A, because that is how much the temperature changed while the reaction occurred. And you're going to get some value for Q. Okay? Now, since the heat gained by the mixture is negative, the heat released by the reaction, we're going to put to calculate delta H, which is our goal, we're going to make Q negative, because heat was released. And remember, when delta H, or when heat is released, the reaction is exothermic, and delta H has to be negative. So the Q, whatever the Q value you got here, you're going to make negative. In E, it says calculate the moles of the metal reacted. So you're going to take the mass of the metal, which was 0.168, and divide it by the molar mass of magnesium. And whatever that is, I'm going to call that letter, I don't know. I'm going to call that letter M. Okay, I'm going to do the math with M. And it says calculate the delta H reaction. Use the D and divide it by the answer in E. Include your units and watch Fig Sig. So you're dividing the negative heat, Q, which is divided by what you got for in E, which was M, and you want the units in kilojoules per mole. Okay? Be careful, because the units here are in joules. When you calculate the heat up here, the heats are in joules because you're getting the specific heat in joules. So you must convert to kilojoules there. All right, you're now going to calculate your percent error. But before we do that, we need to calculate what the actual heat of reaction is. So I wrote down here, I got this from the internet, because some of these weren't on our table. I got the heats of formation for the things in our reaction that I wrote in the beginning. And if you remember, when you're using heats of formation values, the formula, which I'm going to write up here because I need to do some math, and you don't have to write this down, but I'm going to put the value here, and then you're going to calculate your percent error. But find the value, you do the heat of formation of the products minus the heat of formation of the reactants. Well, there's one product, this is an element, so that's negative 196.8, minus the heat of reaction of the products, the heat of reaction of the reactants. Notice that this is negative, but there's a 2 in front of it, so I have to multiply it by 2, and it stays negative. So times negative 1.674, and when I do this math, let me button press, I get negative 46.2 kilojoules per mole. So that's going to go in here. And you should calculate your percent error to see how well we did, and we probably did not do very well. Well, I did not do very well. And I just realized here that I have the case of doing the right math but saying the wrong number. This is negative 167.4. Sorry, I did the right math. I just wrote the wrong number. Please remember that the percent error formula, which I'll just write over in this spot over here, the percent error formula is the measured value, what we got in the lab, minus the accepted value, which is this value here, divided by the accepted value times 100. Okay, so I'm going to go through one of the error analysis questions with you. Because when you're doing error analysis questions with delta H, they can be very, very, very tricky. So the first question is, why is styrofoam a good material to use as a calorimeter? And the reason is that it has a very high specific heat. So it keeps the heat inside, and it itself doesn't gain or take the heat that much into it or absorb the heat. It keeps the heat inside the water, so it prevents the heat from escaping the environment because it has a high specific heat. and doesn't gain heat very well, so it keeps the reaction insulated. So it says if a material that did not have this quality, if you used a material that did not have this quality, will the calculation of delta H reaction be too high or too low? Justify your answer using an equation. So when we were doing the calculations, we used the formula Q equals MC change in T. And if you lose heat to the environment, we need arrows, right? The change in temperature is going to be too low, because instead of the heat going into the reaction or into the water, it's going to go into the air. That makes the Q be too low, right? Because you're multiplying. Now be careful. Remember, you make the Q negative. Okay, now this is going to be so confusing, and I don't know how to make this. Because it's negative, okay, and there's a way to solve this, okay, and then you end up dividing by the moles of magnesium, which is not affected. This value is too low in the formula. Now, normally when it's too low, okay, that makes this equals delta H. That makes the delta H too low. But it's negative, so when it's too low, it actually makes the number too high. So in order to solve that problem of the negative messing it up, so yes, delta H is going to be lower in magnitude. That takes care of the sign. It's going to be less negative. It's going to be less negative. But that less negative number is actually actually higher. So when we deal with delta H being too high or too low, always say if it's too high or too low in magnitude. That gets rid of the negative problem. So again, I'm going to say this one more time. So because we lost heat to the air, the change in temperature was too low. That made the heat absorbed by the water too low. And since the heat absorbed is on the top, or in the numerator, the delta H is lower in magnitude. Okay, that gets rid of the negative sign. So you want to follow the same logic using this formula, using these two formulas, and using the word lower in magnitude for questions 2, 3, and 4. And again, if you need help, you may ask me. Again, you want to try to use this reasoning with this formula and this formula. So this is formula 1, I'll call this formula 2. Which numbers are going to be too high and too low. And then always use the word in magnitude, because that gets rid of the negative problem. Alright guys, I will hear or see you on Monday.